behaves, and we can act different sets. So we can get as many constraining principles as we want to calibrate the circuit. Okay, so this is just to give you a feeling. This is not activity, because it took about 5,000 hours to render the activity. But this is without activity of a circuit with 10,000 neurons. And the reason why I'm showing you this is because when I first saw this, I just wondered, what would be your reaction if you look and you see that? Well, my reaction was, what if we painted perceptions onto the dendrites? Forget about the neurons. Let's paint the perceptions directly onto the dendrites. It's analog. So if you were the maker of the brain, would you choose this to map your perceptions and build your perceptions? Or would you choose this? Would you map analog perceptions on there? In fact, it's known that the voltage-sensitive dye maps, all the maps that have been obtained, even fMRI, MEG, most of those maps are not reflecting action potentials. They're reflecting synaptic activity. They're reflecting dendritic voltages. So we've seen dendritic maps, but why do we only look at the zeros and ones coming out of cells? Maybe you can actually produce specific structures on there. So I'm sure you all know that the current paradigm that we're in is called the action potential paradigm. And it's the action potential paradigm because what it assumes is that what dendrites are doing, all those branches, is that dendrites are processing information so that they will pass whatever is the right thing, the final computed information, to the cell body, and the cell body will now send that to the next one to produce this chain of spikes. And across many, many cells, the spatiotemporal pattern of spikes represents perceptions, whether they're subconscious, conscious. It's the spatiotemporal pattern. You can analyze in any way you want. You can do higher order statistics, anything you want. The pattern of spikes are seen to represent our perceptions, and that's what we measure. That's what everybody does in the experiments. They measure the spikes, and they try and see how they can recreate perception. Well, what if we looked at the opposite paradigm, completely the opposite, and we said, and we make a Copernican-like revolution, and we say, let's forget about this. Let's move from being somacentric to dendrocentric, and say that the information is directly represented in the dendrites in analog form, not in digital form. And let's say the perceptions are formed directly on the dendrites, and that the spatiotemporal pattern of spikes just maintain and animate perceptions. They're just the animators. Just what if? This is just an alternative way of looking at how we may interpret the brain. And let's push this a little bit and see where it takes us. So we know that we can get patterns. We can get maps onto the dendrites. And they go across dendrites. You have to realize that for these, right here and right here, it may be the same neurons, two dendrites, having two different complete properties. Or here, it's a collection of neurons from many different locations. So you are getting dendritic maps across the dendrites. But what happens if you could put intelligence into the circuitry so that you could start painting, literally painting pictures onto the dendrites? This is Ramón Cajal. He's the guy who we had this conference about, who won the Nobel Prize for drawing all these cells. But what happens if we could put enough intelligence into the circuit so that each part of these compartments could be controlled in such a way that you could literally paint 3D pictures onto the dendrites? So it's not that simple because they've only done up to now 2D imaging. But if you go to Amiram Grunwald, who's done most of those, he has in his imagination done 3D. And his imagination has painted these pictures that you have the map, and if you look deeper, there are columns, much in line with Hubel and Wiesel's discovery that you have columns. But more and more, the recordings are suggesting that it doesn't look like that. It more likely looks something like this if you had to do these maps. Now, you have to consider that when you're doing this, one neuron sitting inside this block has dendrites lying all over these properties. How do you get those very specific control of voltages in compartments? So maybe if we did a realistic image, for some reason most neuroscientists just only show bars and stripes and all kinds of things. Maybe if you showed a realistic image, you'd start seeing objects forming inside the dendritic field. And maybe what we really need is topology to help us understand the mathematics of how we build objects for representation. And maybe if you really get it very precise and you can put a lot of intelligence into these circuits, you can start building little people. You start building scenes. And then what you need is you just need spikes to animate these little objects. And it could be that they even become real complex scenes, analog scenes across the dendritic space. So we did a very quick simulation just to play with this idea. We took the dendritic column and voxelized it and threw away the neurons, okay? And take each of the voltages, and we mapped the voltages collectively within a voltage into each of these voxels. All right? So we're just looking at the brain now as a block of tissue. You've got to remember that 90% of your brain is just dendrites. So we're looking at it as a block of dendritic tissue. This is what happens if you disconnect it. There's no intelligence. You disconnect the circuit, and you just do Poisson stimulation. Nothing interesting. It follows exactly what's the pattern of Poisson stimulation and which neurons you stimulate. But now you just connect it. It's not connected intelligently, but you just connect the circuit. And what you immediately start seeing is the formation of complex structures or objects. Something that deviates from just a simple structure. So here it's just showing you. Let me go to another one. That's just a single voltage where EPSPs are occurring across a single voltage range. But this is where you have two different voltages, so you can actually see that the complexity of these objects could actually take on several different forms. And you can actually see there that they do cluster. So somehow the voltages across dendrites coming from different neurons, even when you just do Poisson stimulation, if you have a circuit with some form of connectivity, they start clustering. So what happens if you could really put intelligence into those circuits? This is just to give you a feeling that actually if you zoom inside there, it's not just that it's an object. It's not just that it's a chair. It's an entire universe. You could actually have a whole scene of inside a region of dendrites. So we did experiments, and actually this is totally coincidentally in parallel in another part of my lab for other reasons where we're studying plasticity. We did an experiment to see whether it's possible to rewire the circuitry to insert intelligence into the circuit. So we patch 6 cells, and we see how they connected. So we can define the circuit. Now we take the pipettes out, and we wait 12 hours, and we repatch it. And what we found is that the circuit was different. Not only after 12 hours, but actually after 4 hours. And just to show you how much inertia there is in the current scientific paradigm, Nature said that this was not interesting. Science, I sent it to Science. They said, not interesting. So this will come out in PNAS in another 2 months. So we do these recordings, and we puff glutamate now. Not just, we actually activate the circuit. We can't still put intelligent stimulus, but we activate the circuit. And when you activate the circuit, here you can see that you have connections you have connections appearing, and you have here connections disappearing. This is potentially the substrate that Jerry Edelman could use in all kinds of restructuring of the circuitry. This is happening. We've done this now over a 4-hour period. You can still see the circuitry is dynamically rewiring. For 50 years, we've studied only how synapses are getting stronger and weaker, not how the circuit restructures itself. So it is possible through experience, through stimulating